So let's continue. Our next speaker is Doug Carson. He works at Keysight Device Security Lab. Doug Carson leads hardware security solutions at Keysight Device Security Lab. He's specialized in side channel and fault injection since 2016. The stage is yours.
Okay, thank you.
Should be okay. Sorry, I'll take the sorry.
Okay. Okay. So first of all, let's define what we mean by security in a chip context. It's not about securing toothbrushes or cuddly toys. There are four main industry segments that are particularly concerned about the security of chips and the infrastructure that they're going in. The first one, obviously, is in semiconductors themselves. We require secure enclaves on ICs. We require trusted execution environments to boot the system. Cryptography is now a key part of most secure ICs. And we're also looking at the migration to post-quantum cryptography as well. We need to protect the supply chain and the foundry. That's something that's not often considered, but the massive machines that are inside the foundry have millions of moving parts from hundreds of suppliers, and all that has to be ensured as well. And then lastly, as designers, we have huge amounts of sensitive IP to protect. So we're very concerned about protecting the chips. In aerospace and defense, they're very concerned about protecting against reverse engineering, because if an adversary can get access to the information, that could give them a competitive advantage. They are super concerned about supply chain threats because there's very little sovereign capability to build chips anymore. Most of it is in Asia Pacific and some in the US. Secure comms is obviously an interesting one, and the chain of trust within systems as well. If there are multiple components inside a system of system, how do you include this as a chain of trust? In commercial communications, one of the big ones actually is eSIM. We do a lot of testing in that area. That's going to be the foundation of a digital wallet. So your digital identity is dependent on a secure chip in your handset or your IoT device. Network equipment and IoT devices, really important ones, have those secure. And ORAN, radio infrastructure, because you're mixing and matching, you no longer just have two suppliers. You need communication throughout that. And then lastly, the data center. We have hyperscale data centers, but how can you be sure the pieces that are in there? How can you be assured that this disk drive isn't collecting information? So there's a process called OCP Safe, which is an assessment capability, which is done by the Open Compute Platform to assure devices that go inside data centers. And obviously securing AI models is a big one. And then within a data center, you want trusted platform modules so that you've got full lifecycle protection. When you scrap the server, there's nothing on it. You can't spoof that device. You can't use it to get access to a big data center. This has been recognized at vendor level, national level as well. I would encourage you to read that report. It's by the National Cybersecurity Centre, but it's actually by the Research Institute in Secure Embedded Systems in Belfast. This is a joint US-UK report about the security of global semiconductors. And they've identified 9 challenges in security of hardware. And they're in 3 lanes. The first one is globalization. We've already talked about supply chain. How do you secure things across the life cycle? How do you secure the system? The other interesting one is packaging. We've talked a lot during this conference about things like chiplets, where we've taken multiple pieces of IP, gluing them together. How do we make sure that the entire system's secure? There's a concern about side channel, and I'll talk a bit more about side channels in a minute. There's the fact that things are complex and fundamentally unknown. What does a hardware bill of materials look like in that environment? And then lastly is the ability to scale up. Is secure by design feasible? How far are we going to get there? The role of AI and ML, that's another recurring theme in this conference. And then lastly, the skills shortages. It's well understood that there has been a decline in engineers that have engineering skills, particularly hardware engineering skills, in terms of the number of graduates. So the number of graduates is increasing, but the number of graduates that have electronic skills are there. And if you try to do the Venn diagram of security plus hardware engineering, it gets vanishingly small. So a top tip if you're looking for your next area in career is one area to look at. And just in terms of that, lots of big agencies at a governmental level looking at it, and all the big producers as well. So, I'd encourage you to look at that report. It's quite eye-opening. So how do you exploit hardware vulnerabilities, and why should we care? The bad guys have a 4-stage kill chain. They will try and understand the device itself. They will then try and break into the device using any vulnerabilities that they find out. And then lastly, they'll attempt to reverse engineer the device or the subsystem that's there in the hope of finding something that's a scalable effect. That might be a cryptography key. It might be the reverse engineering of the source code that could spoof and reuse. It could be anything. And that effectively gets fed back through the life cycle. So that could come back as a cryptographic exploit, a hardware exploit. It could be something that would be put in the firmware and the bit stream. It could be stuff that's exploited over the air. It could be tampering in a supply chain. We've already talked about IP theft, or it could even be reputational damage. Hey, this fantastic chip, it's rubbish. You can hack it easily. Here's my YouTube video. It's quite easy to go after, other competitor stuff. And then lastly, societally, credential theft, a big issue in spoofing. So there's no limit of things that can happen there. So the chances of exploiting it are relatively small compared to the sort of vulnerabilities you get in the software. But in terms of the overall impact, if you get hardware vulnerability, it's much, much higher. So it has quite a high risk profile. Oh, that one. Right, so how is hardware hacked? This is a model from Virginia Tech. It's a joint paper we've done with them, and it's quite an interesting model to think about it. When we think about this IVA, we would normally think about software vulnerabilities, buffer overflow errors, etc., etc. There's a level below that, which is the microarchitectural level. That's the intellectual property you would buy from ARM, for example. You're buying an architecture, you're buying a microarchitecture. There are vulnerabilities at that level as well. Spectre and Meltdown are good obvious examples of a microarchitectural vulnerability. Then we have vulnerabilities at the logic level, which are inherent things like timing races, setup and hold violations. And then lastly, where it gets more interesting is the world of physics, which is kind of where I come from. I work for a test and measurement company. We measure things, we measure the real world. So underlying, I always talk about this as the nanoscale attack surface. This is a CMOS, it's complementary oxide semiconductor. That's an inverter. One transistor switches on, one transistor switches off. And in the middle, you're going to get a spike in that current. What that means is within your execution patterns at the top level, there's going to be a Hamming weight that comes down for that. How often do things change? So there's a microarchitectural signature. And at a logical level, that will come out as an observed physical phenomena that might achieve itself as an induction from the ground plane, where we would see induction spikes. It might be as simple as putting a shunt resistor in the power supply and finding current spikes. And then there's other things that we can do as well. So from that side channel analysis, we can now sort of understand what's going on in the device. We can go as far as firing infrared lasers on the underside of the device to work out where the activity is, and then place down into the submicron level to understand where the activity is and do side channel measurements. Once you've understood what's going on, you might be lucky, you might be able to extract keys, and there's a good body of work on that. The other areas is that you can start attacking things. So if you introduce an electoral transient, that will turn into a bit flip in the microarchitectural level. And that could be, you could change data, you could change a value in the bus, you could change a value in an instruction. So what you think is a perfect program, you've turned into imperfect. And a good example of that is a bootloader. There'll be a hash on the bootloader to say, okay, this is signed, is it yes or no? Because 0 is a magic number in Linux, all you need to do is flip the bits to be all 0, and at that point it says, yeah, they match, even though they don't. And at that point, you've got root access to the device. There's lots of other ways to do it. You can do that through photoelectric stimulation. You can use a laser, so you can fire photons into it to induce a current. You can glitch the voltage, you can glitch a clock, and you can use electromagnetic induction as well. So really the kill chain is exactly the same, as the bad guys. To hack it, you understand what's going on, hopefully maybe find a key or find the vulnerability, and then go and try and break into it on the other side. So obviously you want to be able to detect that. What's interesting is that we're now seeing in the verification levels up here, we're seeing a mix of what we're seeing down here. And what you can do is try and predict at a logic level what's going to happen at the physics level. So try and predict the vulnerabilities down here by simulating at a logic level. And I'll explain a bit more about that, but it's really down to do about the Hamming weight that's in it. So this is a new area of verification. It's kind of at the logic level, but it's trying to do prediction of the physics at a lower level. So to break the hardware security kill chain, standard pen test mantra, to know your enemy, you must become your enemy. So for us to work, we have to do hardware penetration tests. That's what we do. And we use fault injection and side channel analysis to do that. The ones that are interesting in terms of verification are, we can look for power leakage, we can look for leakage in the timing domain, we can look for electromagnetic leakage, because those signatures leak in the logic level. Once we've got that, we can do automatic signal analysis and acquisition, and then we can do cryptographic test vector leakage. So we can start looking for leakage of keys. And this is how we go about it. Let's say we're trying to understand that a crypto service is secure. So it might be an encryptor on a chiplet inside a bigger design, or it might be encrypting traffic between two different subsystems. The cryptography might be AES as a well understood standard, and there are test vectors associated with that from NIST. So basically, you put these vectors in, you would expect the other vectors to come out the other side. And what we have are machine learning models that sit on the other side of that are tuned to look for leakage. So those models can start looking for that leakage, and we can start predicting what the keys are. And if we can predict the keys, then there's a vulnerability, and then you have to start thinking about how you break it. So we put the test vector is in there. We have a test fixture at RTL level that we can just take in the test vectors from NIST, and then we're integrated with the EDA toolchain. We do some EDA work, but we're not an EDA supplier. You know who the big guys are, because they can do RTL simulations and they can do power simulations in there as well. The net result of that would be a VCD file. So you're going to get, a very, very long trace file coming out there. And at that point, we can start bringing in a side channel leakage assessment. So the same tools that we use in the physical world, if we were to jump onto a shunt resistor, we can now take in a VCD file and then try and predict what the physical phenomena are, and then start bringing in the prediction models to detect if there's leakage. So that should give you a test versus leakage assessment at the other point. And it also means that once you understand those vulnerabilities, you can go in there. Also, if the chip's already leaked, already working, you can go into the physical measurement and then rerun that simulation against the test vector. So you've got the option of going physical or virtual. The other nice part about that is once you've got the leakage assessment, because you have the netlist, you could go back and do root cause analysis. So what are the hot points in the network? Which ones should be concerned? Where am I going to start doing the work? Because there's no point in saying you've got a problem. Well, yeah, I knew that. How do I actually go back and find out where the problem is? How do I do that root cause analysis? Okay. And lastly, you can get feedback on the RTL. Okay, I'll skip that one. And then we'll do a snippet of VCD file, because these are the things I'm worried about. So this is the clock changing. We've got one clock cycle here, and you can see a couple of signals. This one is moving twice. So that's perfectly not logical. If there's lots of banks of combinatorial logic, you will get that. But the fact is that's going to be driving the transistors fairly hard, and it's going to give a power signature. And if you go in with your timer resolution, what I want to count is the number of those glitches that happen. So in this case, we've got 8 glitches in a timestamp and here as well. So basically, that's the Hamming weight within a time. And that gives a proxy for understanding the power consumption, and then we can use our standard models to go back and do that. So this is an example of an FPGA simulator. This is the initial Revit one, and this is a Welsh t-test. So at 5%, we've got lots of leakage. You can see it's above those red bars. Let's mitigate that. Lots of countermeasures. You can download these slides, so you can go through that. Good example is OpenTitan from Google. That's an open source core. It'll actually tell you design guidance, left as an exercise for a reader. So there's things that you can do to make my life a misery. Easiest one is just to make the data pass 32 bits. So now, if it's 8 bits, I have 256 combinations. Now I've got 4 billion. Now we'd have to throw multiple GPUs at it to reverse engineer. So basically, it becomes a circle of working out where the stuff is, putting back your countermeasures in those, and then going back to the leakage in there. And you can do that all pre-silicon. And this is the both before and after. So you can see the Welsh T value here. This is basically the correlation between predicted leakage and actual leakage. This is rubbish. We've got lots, stuff that's kind of below the 5% level. If we put in those countermeasures, you can see that the leakage, there isn't any at the 5% level. So it's going to be extremely unlikely you're going to detect an encryption key. And to prove this isn't all vendor hype, we want to, so we're not marking and going homework, we've done some verifications on the physical world and the logical world. So we've done a double-blind test effectively. So this one here is the actual measurements from the FPGA for various parts in the netlist. And these are the most leaky signals from the simulation. And you can actually see that there's like 100% correlation in there with one false positive in the top there. So, we're pretty confident that our predicted simulations match the real world. Lastly, this is how we go to market. There's a lot of moving parts in these things, but we start out by doing training and education services. We have certification services that can be offered to vendors, and we run assessment services. So we do eat our own dog food. We do use our own tools, and we're ISO accredited to do that. The pre-silicon capability comes in here, which is an inspector software tool set. And then lastly, we have a hardware stuff there. Final slide. Okay, so in summary, break the kill chain, employ countermeasures, identify power and timing vulnerabilities, and we want to be concerned about hardware security. Questions?
Let's give it a round of applause.
When you're talking about the simulation results, you mentioned RTL simulation, but then you show a diagram of timing simulation. Do you actually mean gate simulation? Or are you relying on delta delays for your combination logic?
Delta delays. If you have a specific question, go after me, because I can put you in touch with our experts to get you an actual value.
So one of your slides, you showed a slide saying RTL simulation, which appeared to have glitches on. The next slide said timing simulation, which would have been
yeah,
so I can see where you get the values from through the gate simulation. I was struggling to see where you got them from.
I can I'll give you an example in a VCD file, and we'll compare notes. But yeah, so there's some slides here that I'm showing. But yeah, and then I can put you in touch with the engineering guys that done it. Yeah, because there is a slide further back that I skipped over that showed the different net lists, timing simulations, etc. So, there are pros and cons in each thing. That's not going to go backwards.
Sorry, I've got an online question. I can take you back if you'd like. If you need to go back.
That's okay. I'll take this one offline.
So with regards to scaling up, do your current verification methods allow OOP-based programming models to abstract and refine down to primitive transitions? Sorry.
Currently not. So we do it more at the test vector level at the moment, but that's that's our bread and butter, and it's sort of level of test we do for the tests that we have for cryptography test, FIPS 140, etc. So that's the point we do. We tend to do less simulation end to end.
Okay, thank you very much.
Thank you.